Alrighty, the grand finale of Introchem. This is week 16, chapter 11, gases. So you can imagine as we wrap up the end of this semester, we had week 14 with solids, we had week 15 with liquids, and now week 16 with gases. All mathematical chapters, all dealing with moles in some capacity or another. So in this chapter, we're going to look at gases, and gases are unique because they're all around us. So we're going to look at the pressure of those gases and how pressure is created from those gases. We're also going to look at the relationship between variables of gases, whether it's pressure, or volume, or temperature, or moles, or all of the above. And then we're going to see calculations of molar mass or density using these ideas as well. As we wrap up this chapter and the semester, we'll look at initial and final conditions of gases. So what happens when you take a basketball and you leave it outside in the wintertime? It loses its balance, but what does that really mean? So those kinds of before and after problems we'll see as well. And then lastly, we'll start looking at stoichiometry of reactions that produce gases or that use gases. Give a little credit where credit is due. A lot of people contributed to this area of gases. Robert Boyle, same person that gave us the scientific method. Back in the 1600s, he was studying a lot of pressures and volumes of gases, so we'll see those relationships coming up. We have Charles, who did volume and temperature comparisons of gases. And then Avogadro gave us Avogadro's number a few weeks back, but long time ago in reality, and he does volume and number of molecules, or what we would call moles. This chapter has a lot of assumptions, and one of them is an ideal gas. An ideal gas is like an ideal significant other, an ideal exam that you get 100% on with no effort. Those aren't things that happen, right? If you want to get 100 on an exam, you're going to have to put in some work. Just like if you have a partner in life, you're going to need to put in some work to that relationship in order to get it to work. There's nothing that is perfect without some work. So as we apply this idea of ideal, which doesn't exist, but if we approach it as an ideal gas, it does simplify the math a whole lot, which makes our lives a whole lot simpler in Introchem especially. So for gases, we're going to assume that they are point-like particles and they do not interact with one another. Therefore, we throw out the entire polarity and intermolecular forces chapter. So it's true that as molecules attract to each other, they can condense. They can eventually freeze, and we're pretending that that cannot happen when it definitely can. We're also going to pretend that they fly in straight lines when they collide with something, and that's also not true. If that were the case, then you'd never see tornadoes or hurricanes, and definitely see plenty of those, unfortunately, throughout the year. And probably one of the biggest assumptions of the three, although the first two are pretty big in themselves, is that when they collide, it's elastic and there's no energy transferred. It's like saying if you run into a brick wall, you don't get hurt. If you have a head-on collision with a deer or with another car, neither car is hurt, and that's definitely not the case. So as molecules bounce in each other, they do transfer energy. We're just pretending they don't, because it makes the math and the physics of what they're doing a little bit easier. So it is a model, just like the entire textbook is models of ideas. We're assuming that they cannot change phase. We're assuming that intermolecular forces aren't occurring when they are, and when they definitely could become a solid or a liquid given the right kind of temperature. We're just pretending that that cannot happen to make it simpler to think about. So even though we have all these assumptions, it actually turns out pretty close to reality, and we'll see that in our final experiment of this semester. So even though we're dealing with ideal gases, or at least pretending that they're ideal gases, they're pretty close to real gases in the end. The four variables that we're going to see in this chapter are going to be pressure. Just got to make sure that they're in the right units. We're going to see volume, and we have to make sure they're in the right units. We're going to see number of gas moles, So if we have grams, we're going to use the periodic table to convert to moles. And then temperature we use in Kelvin, which we've seen in the temperature conversions of exam 5. Everything in this chapter has to be in Kelvin or it's wrong. If they want Celsius answers, you have to use Kelvin in the problem and then reconvert to Celsius in the end. So Kelvin has no negative temperatures, and that prevents us from having to deal with any kind of negative pressures or negative volumes that cannot exist. So using these units, we just do some unit conversions. One of the unit conversions of this chapter will be pressure. Pressure is the force exerted by air around an object. So you can imagine that if a container is open, you have equal pressure, equal number of molecules pressing in as pressing out. If you vacuum the air out, notice there's less and less molecules pushing out. The same number of molecules are still pushing in, and that collapses the canister, crushes the can. We'll see that in lab as well. You can imagine that the reverse is true. If we were to take air and now fill up the container, so if we were to put the air back in, we could imagine that container now getting a whole lot bigger so that it starts to swell up and eventually break because we're putting too much air back in. So that inflation deflation is changing pressure, just like airing up a tire, deflating a tire. If you take molecules out of the tire, it goes flat. If you put too much air into the tire, it could pop. So changing pressure is just changing the number of molecules pushing out versus the ones pushing in. When we look at pressure units, we have lots of different English and metric units to deal with. All of the units at the bottom are equivalent, so you can take any two and do a conversion with pressure units, and you'll see that early on the front page of your homework. Torricelli, one of the few lady scientists we get to talk about in Introchem, came up with the first barometer. She realized that pressure was measurable because the amount of molecules pushing down forces the mercury up the tube, and then if there's markings on that mercury, we can measure those and see how it changes, say with the weather or with condition changes. She realized that 760 was normal, so given her last name, they named 760 Torr after her. Upon the creation of the metric system, they just converted that to millimeters of mercury. So those two are basically one and the same. It's the origin of the unit and then the metric system adaptation of it. If you were to go to Canada or Mexico and listen to the weather, they're going to move that over a decimal place and do centimeters instead. As soon as we jump borders and go to the United States, we're going to have to deal with inches instead. So when you hear the weather, you might hear 30 inches of mercury. The change in the barometer can definitely predict weather patterns and so forth. So you'll see that rising and falling. It also happens to affect fishing. And then go figure, they call all of these 1 atmosphere. And that's the unit we'll typically use in a lot of our problems, 1 atmosphere. We also see that it's relative to PSI, which is not too useful for our class in Introchem, but it is something that you might measure, say, in a basketball or a tire on your car. The other variables that we're going to have to deal with are volume, and volume needs to be in liters. If it's not in liters, it's going to have to be converted to liters. So if it's in milliliters, you're going to have to convert from 1 liter to 1,000 milliliters and vice versa. Temperature has to be in Kelvin, so if you're in Celsius, just add 273. If you're in Fahrenheit, you'll have to convert to Celsius and then add 273. And then moles is determined by either given or by mass. And mass you can get from the periodic table to convert to moles straight away. So let's do a little bit of conversions first to give you an idea of the conversion issues of this chapter. So if we look at gallon of milk, if we look at temperature, and we look at pressure. So what is the Kelvin temperature? Well, if we have 25.20 Celsius, we can add 273, and that'll give us, about 300 and 298, I guess. So almost 300. 0.20. We weren't specific on how we use this, so we'll probably drop off those 2 decimals because we're probably rounding to the tens place. So about 298 Kelvin, close enough. That's the one that we would use for the conversion. And again, we're stopping here, and we don't have to round up with a 0.2. We didn't use the 0.15 of 273, so we can't keep those extra 2 significant figures of 25.20. What is the pressure in millimeters of mercury? Well, if we have 1 atmosphere, you would go to that previous slide and see that in 1 atmosphere, there's 760 millimeters of mercury. And then those cancel. So it's just 760 millimeters of mercury. What is the volume in liters? Well, we have a half a gallon. So we cancel gallon. Brings back painful memories of all those previous chapters that were on exam 5. This is no different. This is the same stuff. That's why we keep these chapters together. For every 1 gallon, there's about 3.78 liters. And then we can take 0.5 and times by that to get liters. So again, about 298 here, they use the 0.15 conversion, so we can keep the 0.35 in the end. Definition-wise, we didn't really have to do the conversion. I just wanted to practice it with you. 1 atmosphere is 760 by definition. And then if you take 0.5 times it by 3.78, you get 1.89. 3 sig figs, 3 sig figs, so we keep 3 sig figs for that multiplication division problem. So as we move towards the ideal gas equation, we'll catch that in our next video. See you then.